In this video, we will do an example that is secretly a definition of a derivative in disguise and talk about how do we recognize that limit as being a derivative. So the example is the limit as h approaches 0 of the cube root of 8 plus h minus 2 all over h. And this represents f prime of a for some function f of x and some x value a. And our goal is to find f of x and a. So in this case, this problem tells us that this limit is a derivative, a certain derivative of some function and some evaluated at some number a. So we have two forms for the definition of the derivative. One of them is a limit as x approaches a, and the other one is a limit as h approaches 0. And out of the two, this looks like the second. This looks like the limit as h approaches 0. That's how I want to begin. This looks like f prime of x using the definition, the limit as h approaches 0 of f of x plus h minus f of x all over h. And one slight modification that I'm going to make to this is this limit is supposed to represent f prime evaluated at some number a. So anywhere there's an x in this definition, let's just write a instead. So let's write f prime of a here, and let's write a plus h inside of that parentheses. And inside of this last parentheses, instead of x, let's write an a. Okay, so we think our limit looks like this definition of the derivative. So now if we match our limit with this definition of the derivative, in particular, that means that this cube root part should sort of match up with this f of a plus h. So f of a plus h should be equal to that cube root of 8 plus h. So the thing that's on the inside of the cube root, this has the form of some number plus h, a plus h. So from that, it seems pretty likely that a is going to be 8. But what's our underlying function here? Well, the 8 plus h is being plugged into a cube root. So our function is the cube root of x. Okay. But to check this, so at this point, f of a plus h matches up perfectly with the cube root of 8 plus h, because that's how we sort of determine this. But let's just make sure that f of a matches up with the 2. So let's check if f of a equals 2, because we need this part to be equal to that 2. So let's plug in 8 into our function. So if we do this, f of a is the cube root of 8, and that is 2. Okay, so this checks out, which means this is our answer. This limit right here was actually representing the derivative of the cube root of x at 8. So in section 4.1, we will learn a shortcut for doing derivatives like this. So if I needed to take the derivative of a cube root of x, what we could do is we could rewrite that cube root of x as being x to the 1/3. And it turns out that there's a shortcut for doing derivatives of things like x to a power. And we'll learn that in section 4.1. And it'll turn out that where the shortcut actually comes from is by using this limit definition of the derivative. So the shortcuts themselves aren't even possible without this foundation of the limit definition of the derivative. And that's why we do this first, before we learn those shortcuts, because we want to remember, where did this all come from? What was the foundation? All right, so in terms of our goals for this section, we have talked about how do we recognize when a limit has the form of the definition of the derivative. In the next video, we will define what it means for a function to be differentiable and discuss what differentiable functions look like.